Hello. Let's talk about the idea or the concept behind mathematical induction. Let's say that there is a ladder that will take you one step at a time to the stars. And you want to prove that you can reach the step where the stars are. So you want to prove that you can reach here. So in real life, first show me that you can start on the very first step, that you can get there. So that's what we call the basis step. That what you claim is true at the beginning. That the if we define so logically speaking, if we define a predicate that returns true or false based on whether you or not you are at a given step. So P of n means are you truly at step number n or not? So prove to me that you are truly at the first step. Prove that this property is true here at the first step. Next, show me that you can jump from one step to the other. So let's say that you are at the generic step number k. You are here, where k could be anywhere on the ladder, including the first step. Show me that if you are at a given step, let's call it step number k, that you can jump one step forward. Because if you can't, then your claim that you can reach the star is invalid. But if you show me that you can jump one step at a time, and you can show me that you can start the trip, then you have given me sufficient proof that eventually you are going to reach the star. Because if you can jump from one, if you are here and you can jump there, then you can jump there, then you can jump there, and you keep jumping like a jumping jack until you reach your goal. So that's the idea behind mathematical induction. Notice that mathematical induction deals with uh, facts or predicates that are evaluated at discrete steps. So we use integers to refer to each step. It's not a method that we can use to prove properties about real numbers or any continuous domain. Excuse me. So let's now apply this to an example to see how it works. Let's say that somebody claims that this expression n cubed plus minus 7n plus 3 is divisible by the number 3. That means it's a multiple of 3. And the claim is that this is true for all integers greater than or equal to 0. So how do we prove it? Definitely we're not going to use exhaustion method and test this predicate for n0 and then 1 and 2 and 3 and all the way to infinity. That's impossible. So apply mathematical induction. Let's prove, so first let's define the predicate. The predicate says that, so the predicate is always a function of a single integer. The predicate says that n cubed minus 7n plus 3 is divisible by the number 3. We have to clearly write the predicate because we need that formula shortly. Divisibility by 3 can also be rewritten as saying that this is equivalent to saying symbolically that 3 divides the expression n cubed minus 7n plus 3. So this is the claim, and we have to always say that this is true for given range of the integers. So we are told that this is true, or the claim says that this is true for starting from 0 and on. So according to mathematical induction, let's prove that we can be, or we are true at the first step, and that's called the basis step of the proof. That to show the property or the predicate is true at the initial value, whatever that initial value is given. So it doesn't have to be 0, by the way. Sometimes claims are made for integers greater than or equal to 13. So your basis step is to show that the property is true at 13, whatever the initial value is. So our n cubed minus 7n plus 3, if we substitute n equals 0, this is a notation in math that says substitute the expression for the value n equals 0. This expression equals 0 cube, I'm gonna be very boring here, 0 cube minus 7 times 0 plus 3. And this evaluates to the number 3, which is a multiple of 3. Or let's say which is divisible by 3. The property says that something is divisible by 3, and definitely 3 is divisible by 3. So I can easily conclude, therefore, P of 0, the property at n equals 0, is true. Please do not say P of 0 equals 3. The predicate evaluates to either true or false, not to a number. So P of 0 is true. And that concludes the first step, that I am at the first step of the ladder. Now, I'm not done yet. I still have to do the step where I can prove that I can jump. This is called the inductive or the induction step, whatever you can call it. So I'm not very keen about terms here, but you can call it induction step, inductive step, whatever. So in that step, again, it's to show that this is a universally quantified proof. To show that for all k, so I'm going to use the symbol k to refer to a generic step on the ladder. For all k greater than or equal to the initial value, again, I have to use the same initial value that is given in the claim, that if the property is true at step k, then it is true at step k plus 1. That's what I need to show. And this is a universally quantified statement. So to prove it, to prove this statement, we would say that let k be particular but arbitrary chosen integer greater than or equal to 0, such that what? That this is true, because this is an if statement. To prove it, you assume that the condition is true, and your job is to demonstrate that the conclusion is true, such that P of k is true, to show. So our mission, I'm being boring here, but you have to write this, to show that P of k plus 1 is true. However, something that many of you miss is, what is P of k? Yes, we have written P of n at the top, but now we have P of k and P of k plus 1, so we must write them down. What is the property? What does it mean that the property at k is true? Where? So we have to write that down, because this is where many mistakes happen if you don't write the property. So where the property of k means or is equivalent to saying that k cubed, so I'm replacing every n in P of n with a k, so k cubed minus 7n plus 3 is divisible by 3, and P of k plus 1 means same thing, replace every n in the property P of n with k plus 1. That's why we had to write P of n at the very beginning, so that we can easily compute what is P of k and what's P of k plus 1. So P of k plus 1 means that k plus 1 cubed, I replaced n with k plus 1, minus 7, sorry, here I said n, this should have been k, minus 7 k plus 1 plus 3 is divisible by 3. I have not proven anything yet. However, by laying down this format, I am very on the right direction, and I might have earned maybe 40 or 30 or 50% of the score so far without doing anything but laying down the problem very clearly and indicating what I need to do. So let's start the proof. So the proof start here. Actually, all of this was like a starting point. Since p of k is true, therefore, that's the assumption, by the way, we assume that p, therefore k cubed minus 7k plus 3 is divisible by 3, and I'm going to write that what it means to be divisible by 3, that this equals 3 times some integer, let's call it r, for some integer, let's call it r. Avoid using symbols that you have already used before so that we don't get confused. Don't use n or k here. Okay, so our job to evaluate or inspect p of k plus 1. So going back to the definition of pk plus 1, we want to show that this expression is divisible by 3. So let's inspect that expression. K plus 1 cubed minus 7 k plus 1 plus 3 equals, we want to inspect what this expression can be reduced to. Our mission here is to use this assumption somehow in the proof. By the way, this is called the induction hypothesis, that I assumed that this is true. So my target is somehow rewrite this p of expression for p of k plus 1 so that somehow I make use of the induction or inductive hypothesis into the expression for pk plus 1. Now here is where different problems start to become different at this stage. But all of them try to rewrite the expression for pk plus 1 so that somehow the expression for p of k shows up. So let's see. And this usually means that we're going to do some algebraic manipulations. So according to algebra, if I expand k plus 1 cube, so you multiply k plus 1 times k plus 1 times k plus 1. I'm not going to do that step by step here, but this is algebra, and this results in the following value. So this part equals, let me start on the right here, k cubed plus 3k squared plus 3k plus 1. This is the k plus 1 all cube. You can verify that by algebraically multiplying k plus 1 by itself 3 times. Minus 7k minus 7. I'm expanding minus 7 multiplied by k plus 1 plus 3. I am not going to make any changes or additions or simplification until I look at this expression. How can I get the b of k, this expression, here? Remember, that's my job. Notice that Here I have, let me use a different color, that have a k cubed here. I have k cubed here. I have minus 7k, I have minus 7k here. I have plus 3, I have plus 3 here. So let's regroup these together so that I isolate them. So this is k cubed minus 7k plus 3. I just rearranged these three terms together so that now I can isolate p of k, and then just write the other terms, the remaining terms. So I have plus 3k squared plus 3k plus 1 minus 7. Now, let's see. According to the induction hypothesis, that since this is a multiple of 3, we said that this equals sum 3 times r, 3 times some integer, by induction hypothesis. So this was by the induction hypothesis. What else can I do here? Notice that I can, oh, by the way, this can be simplified to minus 6. So I can, from the remaining three terms, I can take 3 as a, remember, my target is to show that this is, the entire thing is divisible by 3. So if I can take 3 as factors somewhere, that will help. In the remaining three parts, I can take 3 as a factor. So I get k squared plus k minus 2. Remember, it was minus 6 and I took 3. So now I can even further take another 3 factor and say that this is equal to r plus k squared plus k minus 2. By the way, the previous step, not only I used the induction hypothesis, but I also used algebra to factorize 3 from this part. So now this is the sum and product of integers. So this equals 3 times some integer, because sum and product of integers is an integer. So now the expression for in pk plus 1, which we started as this expression, we reached the conclusion that it equals 3 times some integer. So therefore I can conclude that k plus 1 cubed minus 7 times k plus 1 plus 3 is divisible by 3, and this is definition, using the definition of divisibility. So this statement is what I was looking for, that this means that p of k plus 1 is true. So I have just finished the induction step. I started with the assumption that p of k is true, and I concluded that p of k plus 1 is true. So if I mark this result as result number 2 Roman, and up there the basis step was result number 1 Roman. So I have to make this final statement that by the basis step and the induction step, so I'm going to refer to them by the Roman numbers 1 and 2. So by result number 1 and result number 2, therefore the statement p of n is true for all n greater than or equal to 0. I don't have to write the expression for p of n because I wrote that at the top. So that concludes the mathematical induction. Let me reiterate that What makes a mathematical induction problem different from the other is in the evaluation of p of 0, because it will be a different expression. So let me use a different color here. So how you prove the basis step, and how you go from in the induction step, how you go from p of k to prove p of k plus 1. The algebraic manipulations will be different depending on the problem. For example, in the case of summations or products, in order to write pk plus 1 so that p of k shows somehow in the expression, you may need to isolate the last term from pk plus 1, and that will result in show. So in the case of summation or product, if you isolate the last term, you will get p of k and then separate, and then the last term somehow either plus or multiplied, separate. So that's if the problem is a summation or a product. I hope this video helps you understand how to solve a problem to prove something by mathematical induction. Remember that this method can only be applied when the property is defined at discrete values, and we're going to refer to these discrete values as the integers numbers, and they don't have to be true at the very smallest integer 0, but they could be starting from any initial value. By the way, I could give you a property saying that this property is true for all integers greater than or equal to -5. So -5 is the basis step or the starting step. Okay, thank you for watching and hope this helps you.